This week, Wednesday and Friday, we'll talk some things about, I'm going to skip up to chapter 16 and talk about some things in quality control. An engineering topic, but more broadly applicable within statistics. So we'll talk about this on Wednesday and Friday. There'll be a short homework that I'll post. I'll do a couple problems for this chapter, but it won't be quite as much because you're working on your projects and have other stuff going on as well, right? So to finish the term, right? So and then the plan for the final week of class. This is primarily review. Do some summary, put some things together in perspective, talk about what would be on the final, and then do review problems for that Monday, Wednesday of the final week. So actually, this is kind of interesting to me because there's something like quality control or error control that initially brought me to Vermont. That when I was living in Maryland, there was a conference in Stowe, Vermont, a little conference called an International Total Survey Error Workshop. So in surveys, there's errors that happen in many different dimensions. Some people don't respond. Some people don't respond accurately. There's problems listing the population that you don't necessarily cover everybody. So you can try to list adults in the U.S. and you go to the white pages. Some phone numbers are not listed. Some addresses are not listed. People that are homeless or in kind of a unusual, they're renting a room someplace. They don't necessarily show up. And so there's all these things. Plus there's the interaction between the interviewer and the respondent, which could differ depending on race, ethnicity, gender, education levels, topics. There could be this interesting interaction. So all these things come together in total survey error, and high quality surveys try to maintain. The respondents are all doing things the same way. The questions are all worded so that people understand in plain language what it means. If there's a time element, and so on, that can be difficult for response. And so anyway, they had this small workshop in Stowe in the summertime, and it was a great experience. And that, that led to kids then starting to go into summer camps in Vermont because it was fun being up here in the summertime. And eventually a job came open in St. Michael's. I thought, hey, we like Vermont, so I know something to this. But this quality control, right, is really an ongoing monitoring of a process or data collection, right? So ongoing monitoring of the process. Another word that gets used with this is quality assurance. And sometimes you'll talk about quality assurance more as being kind of retrospective checks. How do you prove, as you're going at a certain cut point that things that have happened in the past are okay? Retrospective. A lot of the engineering emphasis is more on the control, that as things are going on in real time, making sure that things don't get out of whack and something breaks down. But this would certainly be used in many areas. The book has many kind of things about a manufacturing process where people are building something, or creating something, or a machine is doing something. That it should stay in a certain specification so that the products that come out are at high enough quality. This also gets done in surveys. Within surveys, telephone surveys, many of the large organizations will have phone systems set up so a supervisor can listen in on telephone calls, right? That every time you hear something, and this might be reported for for quality assurance, when you're on the line with a service representative or something else, that's this process. And in surveys to actually estimate things about the population, that is fairly critical. The interviewers are trained, they know how to ask the questions, they know how to deal with different issues that might arise. And sometimes these things are fairly sensitive, or medical surveys and so on, financial surveys might be fairly detailed. And people will say, yeah, I have this type of investment product or something. They do surveys on people's investments and so on. You need interviewers that understand that so they can deal with that. Right? The quality control, would also be done in things related to, finance, accounting, that type of thing. So that bills that are being paid and things that are being processed are done correctly. This is also done in medical studies. So at the George Washington University, I was involved in this DPPOS, diabetes prevention program, and its outcome study. And they had both the quality control going on and quality assurance. So as every time things would, so in terms of the control, every time a survey form would come in, a response form, a medical form that would have some data in it, it went through a series of checks to make sure that things were in bound, that ages were correct, that dates make sense, that physical measurements, blood pressure, heart rate, and things weren't too crazy. Now this was a population that was diabetic or pre-diabetic, and they didn't have cardiovascular disease. So some parameters would be extreme, but there's limits, right? So you check it all the way along, and if there's an issue, it's a lot easier to go back and try to find an improved value for that or correction versus 6 months later. It also had a quality assurance part where they would sample medical forms and then go back and re-enter the data and compare it to what was there to kind of check on that quality. Some things did come up while I was involved in the study that had to be dealt with, right? That there were 27 different clinics involved, and one of them started to do measurements of, EEG measurements that looked a little bit funny, right? And it was believed that one of the nurses that were collecting the data was putting this little heart square monitor thing on a little bit off from what was supposed to be done. And it produced a little shift in the measurements, right? So these things do, then you retrain, and if it happens again, you maybe have to take a personnel action because they're not following directions, right? So these things go on all the time in terms of that. There are some famous names associated with this. Edward Deming would be claimed as in the statistical circles, but also in management, that kind of pioneered the idea of continuous improvement in a process, continuing monitoring. So any history of post-war Japan includes talk about how the ideas of quality control and improvement were put front and center to help the economy expand. There's another Japanese, Taguchi. I don't know the history about Taguchi. On the statistical side, there's another guy named George Fox, who was the president of the American Statistical Association, that wrote textbooks on engineering and quality control. And so there'd be a number of names within the statistical realm that would also be involved in this, right? And so, before you go into all these statistical methods for control, one message that I take away about this is you can put into a lot of processes of doing things, ways of setting things up to have a higher quality. Right? So before going into checking on the quality, right, first think about reducing errors. Reducing errors by design. So if there's a way to set up the manufacturing process that involves less manual intervention, that's more controlled, that had less chance for things getting out of whack or less strain on the system. If you could set it up that way, that would be better. And so if you get the people trained very well, right, from the beginning, and plan, and then continuous training, refreshers, so that you don't run into this problem with people not understanding what they're supposed to be able to do. That type of planning at the beginning could be better. It's almost like giving a business talk or something here now, right? But in the survey world, right, there's different ways that you could do things to set up web surveys, right? And the different types of ways people can answer, right? Do you put a lot of things on one page, or do you do short pages? Right? Do you do things where people type in numbers, or do you do pull down boxes for categories? Right? Often, if they're typing in numbers, there's a chance for an error, right? And there's just different ways there's different ways to present things. So you maybe on some web forms you can even have it where they type in a number, and it's a number that just doesn't seem very reasonable. You can have it pop up. Are you sure this is the value that you mean, right? As we go into electronic medical data collection, this is an issue, right? Because in the past, when you would have a survey, a paper form that would list blood pressure and everything like that, people aren't going to write down blood pressures of 17, right? But they might type in 17 instead of 117, right? And if you had the paper form, you can go back and look at it, right? But if all you're doing is typing in a number and then moving on, there's no other record. And so, modern advances, although that's very convenient, you have to think about how do you get quality right at the start, right, and avoid errors getting into the system. Yeah.
If it was just something like typing a number, couldn't you write an algorithm or something for the computer itself to highlight any improbable blood pressures?
So for something like that, right, blood pressure below 50 or below 40,
you're probably kind of dead. So,
and or you could have it just pop up every time a number is entered. Did you mean to enter 17? Well, then people can see it and go back and check it, or put a bound. If it's a fairly regular type of number, then not ask them. But yeah, so that's a programming thing, and a lot of decisions, right? If somebody's typing in a bunch of numbers, and I was doing this all day long, and you're continually asking them, "Are you sure? Are you sure?" That it gets kind of annoying. So there's a level of interaction where you want to do it sometimes for people, and then you could think about trying to do this more adaptively. But yeah, so something like that.
And also with the blood pressure sort of example, like Greg kind of I know with I'm a pharmacy tech, and that's one of the things we worry about is testing wrong, or having not doing their blood pressure correctly. Like my doctor mentioned about taking it 20 times because you're worried about the results. Like, is there ways you could reduce that sort of error? Would you want to maybe set it in a doctor's office, or have like you take your own blood pressure but also have it checked by a doctor as well at some point?
Yeah, so if you could get repeat measurements, right, that becomes kind of a check on that, right? And blood pressure is highly variable and kind of can change over the course of an interaction. So, but it's an expense, right, to do it more times. But that's a good example of the idea that, if you think about reducing error by design, you can avoid a lot of the problems. But you do your best, and there can still be problems, right? So once you get everything improved and things like that, we are going to monitor the process, right? Monitor so that you can detect, when things get out of control. When it gets out of control. And there's a number of methods that are described in chapter 16. The first one we're going to look at is 16.1 is called control charts, right, based on the sample average, right? And the book uses a phrase, assignable causes, when you're looking for a source of an error. So the idea is we're going to monitor the average results of a process as it's going along. And we have certain ranges that we think are acceptable. Right? And at some point the average will go off out of that range. And that will be a signal to us that we need to do some investigation, try and figure out, this is called assignable. Right? Can you assign the source of the deviation or the malfunction to any particular thing? It's not so much a statistical term, but in the engineering language would be looking for that, right? And so the idea of control block charts based on X bar is we're going to take over time, we're going to have certain time points along here, possibly even, possibly a little bit less so. K time points. And we're going to sample in objects or products at each time point. And each time compute the averages. And we're going to plot these X bars over time. And there's going to be X bars moving around here. Don't necessarily all go up and down like that. And we're going to set a couple limits. Right? We're going to set a lower control limit and an upper control limit. Lower control limit, LCL, right? And upper control limit. So that there's that if we do get an X bar that's outside of that, it sets up a signal that we think that something's gone wrong. Right? Yeah.
So like to use the blood pressure example, for instance, if the control group would be the lower control limit of like 100 over 50 versus like 120 over 70?
So, well, something like that. I mean, so if, so it's, you're taking the measurement, so I was thinking more of the blood pressure example is more like just a typographical error type of thing. So, but if you had a flow in an industrial process where the water or the pressure is supposed to be kept at a certain range, and you take readings periodically, right, and then they record them. And so each day you take 4 readings at randomly sampled times, put the averages in there, and then at some point you come along, you take a pressure reading, and you get 4 kind of largish values, and the average is above a cutoff. Something might have changed. Maybe too much input, some blockage causing more pressure, and to avoid the thing breaking or causing other damage, you'd want to investigate.
So it's like a tolerance.
Huh? It's like a tolerance. Yeah, right. And so that's the idea. The 16.2 X bar charts. Right. Now, if we have a bunch of measurements, X measurements, if those are coming from our process, are normally distributed with some mean and some variance, and we're going to take a random sample of measurements of size n at each time point. Probability theory. So then we're going to take a X bar I is going to be the average at time I. Then the expected value probability theory of this sample average at that time I is just the overall process average mu. And the variance of this thing is our sigma squared over our sample size at that time. Okay? So the standard deviation of a particular average with that sample size is just sigma over the square root of n. The book gives that a sigma x bar, so standard deviation of x bar, right? And so one control chart idea is called 3 sigma, right? And if we get an x bar I more than the mean plus 3 standard errors, or x bar I is less, 3 standard errors less, right? Then declare the process out of control. Process possibly out of control. Three standard errors is pretty far out. Right? The probability that the x bar I would be outside the limits. If we knew mu and sigma, right, this would be the upper control limit, and this one would be the lower control limit. Well, the chance that a normal is outside of its 3 standard deviation units is about 0.00226, right? So less than 1%, a quarter of a percent. Where does that come from? So anyway, the opposite, we'll say that on the next page where there's more space. The chance that our average is inside these limits, right, is 1 minus that. Right, so 0.994. So most of the time, if we are if the process is in control, it is not going to give you an average that's far enough out. Right? Where did that come from? Well, these probabilities will come from a normal distribution. Right? So if the x is normal with some mean and some variance, right? And if x bar is normal with this mean and the variance divided by its sample size, well, the probability that x bar, the distance from this mu is more than 3 standard errors is the same that a standard normal, right, if we divide by that is greater than 3 standard normal. And the chance that a standard normal is greater than 3 or less than -3 is pretty small. That there's, so between under standard normal, there's 0.9974 area in here, and then there's half of what's left over, so there's 0.26, so there's 0.0013 out here and 0.0013 out there. So if you had a lot of information on a process, and you believe that you knew the mean and standard deviation, you could calculate lines based on a certain sample size. And anytime you got an x bar above or below, right, you would tend to call it out of control and need to investigate. Right? But right, we don't necessarily know the mean and standard deviation. You know, you establish something new, you run it for a while, it looks like it's going well. You don't really know kind of like underlying true mean and standard deviation to use, so we might estimate it. So what if the mean and standard deviation are known? We're going to estimate them from the sample points. And it suggests that we would estimate it from the sample when process is working well. So you're manufacturing something, and you go along, you take a bunch of samples over time, and during that time period, things look like they're okay. Right? The output looks okay, all the system checks look okay. That looks like you're what's in control. Yeah.
Okay, so quick question before
Yeah.
we move on to this.
Yeah.
So 3 sigma, why are we using, like I understand the 3 sigma, but the fact that we're using a z-value of 0.02 is below like 0.05 for significant level.
Yeah. And so the idea from the engineering literature as represented in this book is that if you say 95%, right, then 0.05, you would use, like you suggested, a smaller value like 1.96, but you're just going to end up stopping the process more often. Right? You're testing all the time, and it's really independent whether it makes an error or not. You're going to have a higher probability of stopping, and the industrial, your process is going to stop more. Right? We'll talk about that shortly. That's related to something kind of the average run length before you get an out of control signal. Right? If you make it an alpha 0.05, about 1 in every 20 times, you're going to stop. Right? If you make it like this, the 3, well, it's about, it's about 0.002. Right? The book says in England they use 3.09 instead of 3 there as a multiplier. Because that 3.09 for a normal does produce an error of about 0.002. Right? 0.002, that's about 1 in 500 cycles. You can go a very long time without detecting an error if there's really not, if everything's really in control. So you get to run for a long time and not have that. Right? The idea is if things break and go out of control by a wide margin, you're still going to quickly detect it.
So you're looking at the process, not what's being made?
Well, however you're measuring the output of this, right? So you could measure things along the way in terms of quality, right? Like in the pressure, like you have a tube that has some type of pressure that you could monitor as part of a process. Maybe you're making beer and there's some certain pressure inside of the cans, right? And so you're monitoring that, probably a safety thing, right? And if it's within tolerance ranges, whatever is the standard process there, then you're happy. But as soon as it goes out of whack, you probably want to investigate. Another measurement that you could take would be the end product, a taste measurement, a calorie measurement, an alcohol measurement, something like that, an acidity measurement. So you might have several different things you can monitor over time to maintain quality if you wanted to monitor it. Right? So it could be defined other ways. So what are we going to do? Right? It's not known, right? So let's say we have a K time period. And we take in objects or evaluations per time period. In many cases, it's possible that n is small. It could be 4 and maybe k, 10 time periods. So if you start out with, n times k is 40 measurements over time. It'll cost you money to do the evaluations and check quality, or it slows things down and so on. Samples may not be that big. Right? Based on the samples, the estimate of mu that they suggest is the average of the x's, the average of the averages. So if you add up over all of our time periods, the average in time period I, so we can make where I, the average in time period I. And then, so that's an average for, assuming that all of our data is collected when it's in control, that would give us an average there, right? what do you do for this? Well, they let S bar equal the sum by going from 1 to k of the standard deviations over k. Standard deviation of the measurements in each time period. It says to do those. Now the expectation of this one, right? The expectation of this one will be mu. But there's not, the average of this one is not actually sigma. The traditional S squared is an unbiased estimate of the variance. So if you're trying to estimate S squared, you could do that. So this is one option that they could present. It turns out that though the expectation of this S bar does not actually equal our sigma that we want to know. The expectation of S bar is sigma times some coefficient. And I think that's even an approximation. I don't think it's, I didn't have time to look it up to know if that's the exact value, but it's approximately the value. And I think it's a first order approximation. The issue here is that S squared, or S, is a nonlinear function. Well, it's not a linear function. It's quadratic. It's a square. And so you're taking the square root of that thing, and so it's just, because of the nonlinearity, it doesn't end up being equal. This a sub n thing, right, so I'll write the next expectation of our estimate of S is sigma times a sub n. Now the a sub n, the book gives as a formula. Square root 2. The gamma function that we saw in some of these distributions. So we're getting -1. And there's a gamma function in -1/2 in there. And so our sigma hat that we're going to use is going to be S bar over that number. So that, to at least the order of approximation this is, our estimate, we'll get that bias estimate for that. So it suggests then using a control chart that is, so our control chart limits as presented in the book. That average of the averages over our measurements over time. Plus or minus our 3 value, or if you're in Britain, if you're in England, do 3.09, because they like that. And then we're going to estimate sigma, that average S over that adjustment factor. And then there's a square root of n term there for the n measurements. And that'll give us a control chart, right? Now, from a statistical viewpoint, that's one estimate of the standard deviation. From analysis of variance or other time series models, I imagine that the field really had a lot of other options that they had done for determining that. But this is the one that's presented there, so I'm not going to presume to know any better. It looks a little strange to me, but it's obviously figured out and it's part of the literature. I think it would work quite well to do something. Now I prepared an example. I meant to copy it, but I don't seem to have it. Here I didn't print it or don't have it. So we're just going to have to look at it here, and then if you want to get the handout, it is available as a PDF. So in one of this is a little data set here that comes with the book. The example is 16, too much time here. So the example is problem 1610 in the book. The context of, this is on page 689 or so. This is a manufacturing product facility in India. They're making bath faucets. And the focus here of quality is the threaded stem dimensions. If you get them too big, right, it won't fit in. If you make it too small, it's going to leak. So you had to get it within a pretty narrow tolerance to make it worthwhile. Otherwise, you're really annoyed by this. In this data set, there's 25 time periods. In 4 measurements each time period, so maybe once a week or once a day. Maybe once a day, you pick 4 of the products that come out of the assembly lines randomly during the day and measure them with a very precise tool, right, and come up with measurements. And these are the measurements. There's 4 measurements, 1, 2, 3, 4, across each time. It looks like this will be about 13 millimeters as the width, and 25 different time periods, 4 measurements each. So let's look at this process and see what it looks like. Does it look like it's out of control or not? And so to do this, I read it in. I read in the data. That data dat, right, is read in like this. It has one column there for the subgroup, for the time period. I don't really want to use that. So I'm going to take that one off. This reassigning dat to itself with that -1 there removes that first column. I'm going to drop that one out. I can keep track of 1 through 25. I don't need that extra variable in there. So now dat just has the 4 measurements that are in there. Right. So let's compute the average every time. This apply thing dat is a matrix. It has rows and columns. If I want to take the average across the first dimension, this command does that. Now my x bars, so here's my, oops, wrong place. My x bars are, these are the 25 averages. Here's my histogram of my 25 averages. I want to know, do any of these look like they're kind of out of control, or did something go wrong with the process? I'm going to need the standard deviations as well. So this one is all my standard deviations. Here are my standard deviations. Right. Kind of nice size. Now, eventually there's another method based on ranges. So eventually I'll calculate the ranges. And when I did this, the range gives you 2 numbers, and I'm taking the difference of those. And it seems to, in its basic form, produce a matrix, like I only want 1 dimension. So if I make it a numeric value, it will kind of erase that dimension and just give me a list of ranges. Right? The ranges is the range from the smallest to the largest within a time period. So the A value for 4, there's a list of them in the book for 3, 4, 5, 2 numbers like that. The value when it's 4 is 0.921. Why do you get these gammas and square roots and things? Well, this has to do with the order statistics, which have kind of a combinatoric thing to it, and the distribution. There's a chi-square distribution, so there's some probability distributions that have some of these gamma constants in there. So they show up in this. Within R, you can calculate these gamma functions, these special mathematical functions, gammas, betas, and other things. Right? And so if you just put in a value there, you get a gamma. Right? So these would be the numbers that are according to that formula. And it's 0.9213, so there's a little bit more. I'm going to be all precise here, and my A4 value, I'm going to make that. We're going to do something shortly with ranges, and there's another set of values for adjusting those. So that's what that is. Now the formula for the confidence level, if we're in Britain, we use this 99.9% cutoff, right? And so that value from a normal is 3.09, right? If we did the do the probability that you're less than 3 is that, or the probability that your p-norm large or less than -3. That's our 997, I guess we said 9974 up there, so it just seems to be off by a decimal. But anyway, that's about the value. So if you did this, this would be our lower cutoff and our upper cutoff values, so I'll do those. I'm gonna put it, they would be these numbers, 12.91 up to 13.06. So if we ever get any of these X bars that's bigger than that or less than that, it's out of control. Right? We're plotting, I looked a little bit at the range of the X bars. Right? So the lowest one does look like it's below that, and the upper one does look like it's above it. So it looks like we're gonna get something kind of outside of that range. And I worked for a little while to make a nice little plot here. So I'm going to set it up with the range and a certain range that I want here. I'm not going to plot the points yet, that's what this thing does. But I've changed the X label and the Y label and put a title up here. And then I'm going to put points. I'm going to, from 1 to 25 on the X axis and my X bars on this axis. And those are my 25 means that are on there. If I put my lower limit in there, there's my lower limit. Right? Here's my upper limit. And here's one at just the overall average. Right? Does this process, what do we conclude about this process? If we thought this process was in control and we've computed all these things, it looks like, a couple, 3 of them look like they're greater than or less than that, those cutoffs. Right? And so that would be a signal. So we've collected 25 data points, like we go collection for a month. We look at it, right? Then after that point, say, oh, wow, it looks like things are a little bit more chaotic than we would like. Yep.
So when analyzing these, it was perfectly in control. There wouldn't be any outliers outside of the 3-bar range or 3X bar range.
Yeah, you would tend to think that, if these were down here a little bit, right, inside, they could be, they're not all right at the global average. They're a little bit off, but
It's
yeah.
real life that happens. So
Yeah.
would this be an indicator that you have to tweak whatever process you're using to fine tune it to be a little bit less chaotic?
Yeah, so you probably want to investigate this. Why does on some days, in some periods, this is particularly high, particularly low? Is there something going on with wear on the machinery or the input or how it's being run that's causing this? You probably would want to try to get that in control to dampen that variability. But yeah.
So the purpose of this is kind of to be a quick way to determine how consistent
Yeah.
something is.
Right, so if it's a process where you like in this example with the threaded things that have to fit together, it has to be consistent and very narrowly so. Otherwise, it's going to leak or not fit or just not pass other inspections. Right? Yep.
If this was something more fine-tuned, like let's say a water faucet, would that be a case where you,
What was your example?
like if it was something that needed to be a lot more fine-tuned, like maybe some sort of medical instrument that can't be, or space part that can't be within 1 millionth off or what have you, would you then increase that signal level to be able to, or decrease
So it would adjust, right? So if you're dealing with something on medical tools, if it needs to be within a millimeter, right, or a fraction of a millimeter, I mean, some scientific instruments would be made that precise, right? And so in the calculations, right, of this, right, this is the standard deviation of the measurements in a particular four measurements in this case, right? And so if the scientific measurement is that precise, then this S is going to be very small, and your range of what's allowable is just going to be really small too. It's what adjusts to the scale of whatever thing you're doing, right?
So if you're using the 3 sigma, would you just adjust how many sigmas away is considered out of control?
Well,
Or would you
not
just not use the
necessarily.
3 sigmas?
I would say, I'd still use 3. So two things. Let me go back to something like this, right? So we want to. There's that, right? So two things we can say about that. One thing I want to say is just that there are other options for estimating. Another option for estimating my sigma is sometimes people do things based on ranges, right? And so if you have the range, if R is the range of your data, x1, x2, up to xn, which is the maximum of the values, right, minus the minimum of the values, it turns out that the expected value of this range from a normal sample, you can figure out that it's related to the spread of the normal distribution, but there's this extra, it's not exactly the expected sigma, there's a multiplier on there. The range is more like 4 sigma or 5 or 6 sigma, something like that. So the entire range of a data set is usually a little bit larger. Right? And so if R bar is the average of the ranges across your times periods, right? So R sub I is the range in time period I. An alternative control limit 3.09, and then you can put this R bar over B sub n as an estimate of the sigma, and then the square root of n in there. Right? So that's kind of one side. There's other ways of possibly getting at that standard deviation. If you do it in this case, you did a little bit of, I calculated the ranges of all those time periods. The v-value that's the divisor there is described in the book is about 2. Right? So an alternative way of giving the ranges, oh, it's down here. The space is here so that it prints out nice, but I don't seem to have it print out this way. Here's this alternative formulation of these ranges. The two cut points are not exactly the same, but they're pretty close to the other ones. Right? And if you do that plot of these and put in, here's the averages, here's the two control lines, and this in the middle here. These are still above. A little bit different estimate of S and that range in there, but it gives you largely the same picture. That's plus or minus 2, plus or minus 1. There's some discussion in the book that, well, we'll get to that, but if you had a sequence of averages that were, say, out between the blue and red, or between the red and the dotted ones, that would be between 2 and 3 standard errors away. Right? That also would kind of be a signal that there might be other ways you would look at this, right? This data. So, yes?
If you then went and took more measurements, would you want to do the control and calculate the X bar and the standard deviation with removing the 3 that are out of control?
Yeah, right. So the scenario for doing this, right, can be kind of multifaceted, right? In the sense that, well, what if you did 10 of them and calculated an X bar and a standard deviation? Maybe then you would want to assess, am I in control or not? Maybe this one would stick out based on the first 10, maybe it wouldn't. If it did stick out, say, oh, there was some problem that day that maybe investigated, maybe they changed something and fixed it, right? Corrected something. The book says, well, you would probably want to take that point out because it's making the standard deviations bigger, it's changing the averages, it's influencing things. And if that one's just to be out of control, what we want to compare to is an in-control situation. So the ones that are in error, you probably take out. So you do 10, and you get an 11th point. You think that one looks okay. You probably would recompute the averages and kind of get this running thing going along. get more evidence about what is the standard control and do it over time. I guess the second point then, is that in this decision process, just like hypothesis testing, there are some error rates. So just like in hypothesis, we'll have a couple error rates. We could decide that things are in control, or we could say things are out of control when everything's really okay. Because just by chance, every once in a while we're reading an unusual sample and it's going to look out of control, even though it's fine. If you investigate and find no apparent problem and then run it again and it seems to be the accident, maybe it was just a fluke. So the first error rate is called alpha, just like hypothesis testing. Is the probability that a single sample x bar I is outside the limits. Right. Given that there is some control being maintained. Right. That the process is performing at the desired average level. And if we have the probability that z is greater than 3, or a standard, or z is less than -3, if we're without the 0.0026. Or if we use, as it points out, if we use 3.09 as the cutoffs here, right, then this probability is about 0.002, or 1 in 500. So those are set so you don't stop the process and investigate unless it's really kind of going out of whack. The other type of error, like in hypothesis testing, is called beta, is the probability that a single sample, x bar I, is inside the limits. When, given that, the average is mu0 plus some deviation. Out of control by some certain amount. Right. And so this thing is calculated as, well, draw a picture, very much like we did with hypothesis testing, at a nearest mu sub 0. This is in control. And these are the sampling distributions of x bar. And this is the alternative. This is, if something goes wrong, mu sub 0 plus delta times sigma. So many standard deviations away from that average. We're going to call it out of control if it's up in this red area, this pointing area, right? Say that's 3 standard errors away. So this error is the chance we're inside the limits when we're really over here. So what's the chance that we're inside the limits? The chance we're inside the limits under this hypothesis is this area. And so that shaded area there is our beta. And generally we want that to be small. So that if things do break, we get a high probability, a low probability of missing it. Right. When do you get smaller errors this time? If things break really bad, right? And the two are like completely separated, right? We're not going to be in that area, right? So if we have two alternatives here. This is a slightly out of control. That's going to be hard to detect. Right? The probability, there's still a very high probability you're going to be in your control limits, even under that shifted curve. But this one is way out of control.
You can hopefully detect.
Yeah, so if that breaks, so you're going to be outside of that almost 100% of the time. So you would detect, if you're monitoring it, right, then you would detect it and immediately say that something looks bad. And there's a sliding scale, right? The more out of control it gets, the more probability you get, and so kind of the seriousness of that error.
So
Yep.
with the slight out of control versus way out of control, does that have to also do with variance then from the mean?
Yeah, that will have to do with the variance, kind of this whole spread of things, right? So if you had a sloppy process with a big variance, right, and the wider it is, right, then your control limits are going to be wider. But if you're very precise and sigma is small, right, then your data are going to be close. Your estimate of it, your S, is going to be pretty small, and you can set your limits pretty tight. Right, if it's a really precisely manufactured process. Right?
So with these sorts of tools that help us figure out what's a sign that something's out of control versus not.
Yeah.
Especially with the 3 sigma one, you don't change the 3, you change the sigma, correct? If you're trying to be very precise.
Right. So if something changes in manufacturing, so you get a new tool, so you're able to manufacture things with greater precision. Like you're cutting the metal, right, or molding the metal. You get a new way of doing it that introduces less error. Right. Then the XIs are going to be closer. The X bar and the standard deviation will be less. Right. So if you're, if you had one process here, I'll go this one right underneath, right, this one's more narrow. Right? And say here's u sub 0 and here's u sub 0. And so this one's narrower is the point. So sigma is smaller. You can adjust the process so that it doesn't produce. So you get a more sophisticated scale, right? So you're measuring weight, right? Ordinary scales you're going to go buy at the department store or a grocery store or pharmacy. That costs 20, 30, 40 bucks. Have some variability depending on how you stand on it and something like that. But a doctor's office scale is of higher quality. It's a more consistent measurement. You're step on, step off. It's going to be more accurate to fractions of a pound. At the other end, if you're really interested in doing that, it would be another level up where the measurements from one time to the next won't have that extra variability quite as much. Right? You might affect the variability are you always consistent? Do people wear shoes? Do they, how much clothing do they wear for weighing? That shoes or a coat or something on or a sweatshirt adds a little bit to the weight, and some people have it, some people don't. That introduces variability. So you set standards, you could make it narrower, right? So this is smaller, so then the X measurements are less variable. And that means that X bar is less variable. And then the distance from the lower control limit to the upper control limit is more narrow. You still set the decision rule that alpha, 0.002, right? So that you have a very small chance of making an error and declaring things out of control, which is really true. Right? I guess one thing that we haven't, I wanted you to mention is that there's other things. There seems to be quite a bit that can be discussed. Other ways to estimate the standard deviation, right? There are some supplemental rules. Say you have a bunch of measurements that don't pass the 3 sigma line, but you get 2 or 3 in a row that are, say, positive past 2 sigma, right? So other patterns in this might also suggest that there are problems. And related to that is this thing called average run length. How long would you go before an in-control process shows you something out of control? How long do you have to run that K time period, that's K, before you expect an out-of-control XRI. And so the book gives a calculation formula in there, but if there's only a little bit of break, a little deviation from the standard, it's only slightly out of control, you might have to go 100 times, 50 times, or something like that, before you would expect one. You could, of course, have the next one be out of control, but you might, on average, have to wait quite a long time. So some of these supplemental rules are important if you can't take big measurements, you can't take frequent measurements. So making up other scenarios that would suggest a problem. It's not only making them up, there's a probability content would find them. I bet if you go to a book on quality control methods, it will discuss the probability calculations associated with a lot of different variations, right, that you might look at. Well, I think that's what we're going to do for today. We'll bring up a couple other points. We'll look at 1 or 2 other statistics on Friday.
Professor, was it this class that, I remember one of my professors mentioned going to the academic symposium. I wasn't sure if that was this class or another class.
It's, we didn't say anything particular about it.
Okay.
But it's,
I was just like trying to remember, because one of them was like, oh, we're not going to have class for the academic symposium. I was
there's
like,
no class on Friday.
okay.
Next week.
But I
There's
think
some
that
days-
symposium is Friday.
Is this Friday?
I
Okay.
think so. I
Yeah.
could be wrong. It is.
I don't think we
It is.
did.
It is.
But if most things don't start.
I could be. I could not. Okay.
Yeah.
All right.
Yep,
Just
yep.
making sure. I'm making sure. Really, no, I did introduce Emily. I know she told me after the symposium.
She's introducing me tomorrow.
Yeah.
Yeah.
I have one that I just wondering not really, but yeah, I'm using it.
Here you go.
That's probably that same outline. Just list that stuff on used, like I'm not gonna waste that on auto. So I did like a tree or chart, probably the lines of like the score, like change of 70, things like that.
Well, so good. Yeah, for the collection,
And then like.
related to work or one division versus the other. So does it make more of a difference on one side versus the other? Does it make more difference from home field advantage or home advantage versus not?
That's a good one. Okay.
So if you score first at home, right, you're winning quite a bit better.
Okay.
Yeah.
Cool.
Okay. Yes.
Oh, yeah, shoot.
Go ahead.
Can I meet with you after this class period about tomorrow's homework?
Yes.
All right, cool. Thank you.
I was gonna
Here are
say that.
these.
Oh, yes, thanks.
Could come by as well. Ask it to